Okay, let's remember we were looking at new DRAM architectures. We talked about RAIDer and tiered latency DRAM. I'll give you two other ones relatively briefly. One is to solve an important problem, which is the bank conflict problem, and the other is to accelerate page copy and large-scale page copy and initialization operations. How can we support these better in DRAM? And both are taking advantage of the underlying microarchitecture in which DRAM is designed today. Actually, I'm surprised people have not looked at some of these issues before. Mainly, the problem has been the cost in DRAM, but I think going forward, some of these approaches are relatively low cost, in my opinion, and maybe you can develop even more low-cost approaches that can do other things in DRAM. So the first thing I'll talk about is subarray level parallelism. How can we reduce the bank conflict impact by taking advantage of the underlying DRAM architecture? And we talked about banks earlier, right? And a bank is basically a unit of memory that you can access. And you have multiple banks to enable parallelism and also to reduce latency because you can divide a monolithic memory into pieces of banks. The problem is if you have two requests that are mapped to the same bank, which is determined by your address mapping, which is an important problem in itself, these requests have to be serviced serially. And this is costly in terms of performance and power. If you have many requests going to the same bank, then they're all serialized. Ideally, we would like to reduce the bank conflicts without adding more banks, basically at low cost. That's what we're going to try to achieve. And the key idea in this work is to exploit the internal subarray structure of a DRAM bank. DRAM bank actually consists of smaller sub-banks, subarrays, and we're going to try to access them in parallel as much as possible without increasing the cost. And the way in which we will achieve this will be by reducing the global sharing of hardware structures between these subarrays. If we completely make them independent, they will become banks. But we're not going to make them completely independent. We're going to make them just independent enough to get most of the benefit. And this is described in the Cisco paper. So if you want to read about this in more detail, I would definitely recommend you to read the paper. I don't cover every single detail of the paper. So if you're more interested, there's a lot more detail in the papers in terms of both modeling as well as algorithms. So what's the problem? If you have two banks like this, and if you have 4 requests, let's say blue write and read requests that go to the same row in this bank, and this gray write and read requests that go to the same row in this bank, these are serviced in parallel. Well, I'm ignoring the bus here, address command, address buses here, but these are serviced in parallel within these banks. But there's some serialization that happens in the bus. Ignore that for now. That happens in every system that shared the data bus in the end. So we would ideally like to achieve this. The problem is if you have one bank, what happens is these requests get serialized like this, and they can get interleaved. Remember, memory schedulers try to schedule writes in batches because there's a write-to-read switching penalty. So this memory scheduler is scheduling these writes in batches. It first do the writes to different rows, and then it does do the reads to the different rows. As a result, well, you get first serialization effects because there's only one bank. The second is you actually have write recovery latency. This is TWR in DRAM. And you get the write penalty after every write access, and that serializes everything even more. And also, you get row buffer thrashing, because there's a single row buffer that's being shared by these accesses, and this goes to the blue row, and this goes to the gray row. So you have these 3 effects that actually lengthen the latency. As a result, you get wasted cycles, if you will. You would have saved a lot of cycles if you had just 2 banks. And in fact, this is much worse, but I cannot fit these red portions are much bigger than I depict here, but I cannot fit it on the slide. That's why you have fewer wasted cycles on the slide. Okay, so our goal is to mitigate the detrimental effects of these bank conflicts in a cost-effective manner. There's a naive solution to this. You can add more banks, right? But this is actually expensive. If you add more banks on a DRAM chip, you increase the cost because you add more row decoders. There's another way of achieving this. You can add more channels to a processor, right? That actually increase the banks. But that's actually costly because that increases your pin count on the processor. You can add more DIMMs, but that's also more costly and not scalable. And we covered that earlier, having multiple DIMMs. So we'd like to try to do something with the DRAM chip without actually adding more banks. Basically approximate the benefits of having more banks without adding them. So how do we do that? There are 2 key observations. First is actually, what we have been discussing was a logical abstraction of a bank before. A DRAM bank doesn't exactly look like this. Logically, we said a DRAM bank consists of lots of rows and a row buffer. Actually, we've deconstructed this a little bit when we talked about the tiered latency DRAM. We have actually subarrays, right? So you already know that this is a logical abstraction. Actually, if you look at a DRAM datasheet, you have maybe 32,000 rows in a bank and a row buffer. The problem with this design is if you have 32,000 rows in a bit line, it becomes very, very slow to drive that entire bit line with a single row buffer. So DRAM is actually divided into subarrays physically. You have a bunch of subarrays, each having their own local sense amplifiers, local row buffers. What this enables is you have smaller short bit lines called local bit lines. So when you read a row, what happens is the row is activated and the bit lines start driving this local row buffer, local sense amplifier, and you sense the entire row within that subarray. And later when you do a read, you read a column from that subarray through the global bit lines, which need to be very large because now you need to drive across the chip. You drive the global row buffer. This is the global I/O circuitry. And actually this is much smaller than the local row buffer because the bit lines are much larger over here. So this was an abstraction. Now we're deconstructing the abstraction. So you have lots of these subarrays that each has its own local row buffer. So what can you do with this? Well, each subarray is actually mostly independent. It's not a bank. It's not totally independent, but they're mostly independent, except they occasionally share some global structures. What are those global structures? The first is this global row buffer, global bit lines. Basically, two subarrays cannot be driving. You cannot read exactly at the same time from the two subarrays because they share these global bit lines, the I/O circuitry. And they do have local row buffers, but they also share this global decoder. You don't want to have many decoders for each subarray, then they will become banks. So the key idea is to reduce the sharing of this globals just enough such that you get the benefit of having more banks. Let's take a look at how we will do that. We'll basically reduce the sharing of this global decoder to have parallel access to subarrays. And we're going to reduce the sharing of this global row buffer such that we can utilize these multiple local row buffers. In today's DRAM, you cannot keep multiple local row buffers open. First of all, you're not aware of the subarrays. Memory controller is not aware of the subarrays. Second, if you keep them open, you get a collision because they share the global bit lines. So we're going to reduce that sharing. And that's the idea. So what's the mechanism? Basically, assuming that these go to the same bank, but to different subarrays. The blue ones go to this subarray. The yellow requests go to this subarray. We'd like to try to do this. Basically, parallelize, open the row buffers, and keep them open, such that if there are more yellow requests coming, you can service them from this row buffer. If there are more blue requests coming, you can service them from this row buffer. So what are these global structures? I'll give you the basic ideas as to how you can reduce those global structures. One is the global address latch. Let's take a look at that first. When you actually access DRAM, the address is decoded and latched. And this latch is shared across different subarrays. So let's say you want to do a read to this blue row in this subarray, subarray 0. Its address is latched, and its row is activated. And you can do a read after that, which brings the data through the global row buffer and out of the chip. Now, if you want to do a read to the yellow one now, you have to precharge this subarray, precharge the entire bank, which basically gets rid of the address in the latch. And now you can send the new address to a different row, which latches the decoded address. And then you can actually activate this yellow row, and then you can do the read. So that's the cause of the serialization. Well, if you actually get rid of this shared latch and push it into the subarrays, so after you decode the address, you keep it in a latch that's specific to the subarray. And after you decode this address, you keep it to a latch specific to this subarray. Now you've gotten rid of that sharing of the address decoder. Right? This way, what you can do is you can send the blue address first. It gets latched, and you can activate it. You can send the yellow address next, and it gets latched. And this can get activated too. That's the idea. So the basic idea is move the global latch such that it becomes local latches. And the overhead of that is not that high because the global latch stores all of the addresses. Local latch hopefully stores fewer addresses. But this is part of the overhead of the mechanism. Okay? The second issue is, but this doesn't enable keeping these active and reading from these because in current DRAM, you cannot do a read selectively to a subarray. So that's the second problem we're going to solve. you have these global bit lines that are actually shared between these subarrays. So let me abstract this problem. Basically, you have these two subarrays. We would like to keep each of these local row buffers active, and we'd like to be able to read from each subarray. The problem is it's global bit lines. Let me abstract this way. It's not that way, but I'm going to move that global bit lines outside, and I'm going to abstract them as a switch. So switch can be open or closed. Basically, this local row buffer can be connected to the global bit lines, which means that it can be driving the data out of the chip. Right. Today, there's no control on the switch. When you do a read, what happens is both of these data get connected to the global bit lines. As a result, you get a short circuit. Right. You get a collision. Basically, you get garbage data out. Basically, the idea is to have a designated subarray or designated bit latch, basically, that controls the switch. The memory controller can specify which subarray it's going to read from. So if it's going to read from this blue row, the memory controller can say, okay, I'm going to designate subarray 0 to drive the global bit lines, which sets a bit in DRAM, and that connects the subarray selectively to the global bit lines and disconnects the subarray from the global bit lines. That way, you can selectively read one subarray. And then later, if the memory controller needs to access the yellow subarray, yellow row, the memory controller can designate this subarray to drive the global bit lines and this subarray to not drive the global bit lines. This way, you can selectively read the yellow subarray. Now you can keep open many row buffers, as many as you have subarrays, right? And this is, remember, this is a lot of data. In a row buffer, you can store 2 kilobytes of data, right? Or depending on the DRAM chip. So that's the idea. Basically, by enabling selective connections basically by selectively connecting the local row buffers to the global row buffer or global bit lines, you can enable multiple local row buffers to be active. And the cost of this is a wire to set these designated bits and to decode, of course, which subarray you're actually going to set the designated bit for, but that logic already exists whenever you need to send an address because you need to know which subarray you're accessing internally. But these designated bit latches are not there today. Okay? Okay, so these are the two things that you need to solve to actually reduce the global sharing. And what is the effect of this? We call this a multitude of activated subarrays. This way you can activate multiple subarrays at the same time, and you can read from them mostly in parallel, actually in a pipeline manner. You have to send the addresses in a pipeline way. So what are the advantages? Remember, this was the baseline that I showed you earlier. This is the subarray oblivious timeline of the requests that we've seen. You had serialization, write penalty, and trashing, because all of these happen in a single bank. With multitude of activated subarrays, we should have a better name for this. Although Meza sounds better, I'll call it Meza. Sometimes it's better not to pronounce the entire thing, right? It's easier to pronounce MIPS than microprocessor without interlock pipeline stages, right? Without interlocking pipeline stages. But Meza, what you get is basically pipelined accesses to the different subarrays. As a result, you save a significant amount of time. It's not the same as a bank. Remember the bank picture? It doesn't fit here, but the bank picture enables both of them to start at the same time. Okay, so what is the overhead of this? So we've done some studies to look at the die size increase. It's about 0.15% according to our estimations, which apparently, according to Samsung, who tells us this is a little bit lower on the lower side. So Samsung has looked at this and they found higher overhead, but they found the overhead is not unbearable, apparently, for them. So we'll see if it's going to be interesting enough to implement. And the overhead comes from the subarray address latches and the designated bit latches and the wire. There's a static energy increase if you actually activate multiple subarrays at the same time, multiple row buffers, local row buffers. You're actually increasing static energy, right? And we quantify that. But the upside is we're going to save dynamic energy, assuming you can exploit that row buffer locality. And there's, of course, changes to the controller. Now the controller needs to be aware of the subarrays, right? Somehow it needs to keep track of the status of the subarrays. So this is additional information to the controller. And also, the controller needs to keep track of new timing constraints. So the controller needs to be able to switch between the subarrays, right? And that requires some timing. It takes 1 cycle to switch between different subarrays because they're not banks. Okay, there are actually cheaper mechanisms. You can take a look at the paper. You don't have to implement this in a full-blown way, which covers these 3 different penalties that I discussed. You can actually have cheaper mechanisms that get rid of the designated bit latch. This way, you cannot keep multiple row buffers activated, but you get some of the benefit of this. You can actually have no overhead and try to do something in DRAM, which is discussed in the paper, but you can look at it. You get some benefit of this. Let's take a look at a little bit of the data. So we have a detailed DRAM simulator to simulate this, and we've looked at a bunch of different configurations. I'm going to show you results with one configuration, very limited, but you can look at the paper for more details. And you already know about a lot of these things that we've discussed in the basics lecture. So you can imagine this has an effect. The line interleaving, how you map the data on these subarrays actually has an effect on the performance you get, right? If you map the data address bits randomly to these subarrays, you may not get a lot of locality in the row buffers. So actually, we looked at both line interleaved and row interleaved policies. Remember the cache block interleaving and row interleaving that we discussed in the basics lecture. And this works with different policies, but there could be other policies that can take advantage of this much better. So some results with single core workloads. I believe there are many more workloads, about 55 in the paper. But this is showing the best workloads over here, just to show that where this works. And where this doesn't work is discussed in the paper also. But you can imagine, we'll discuss that. This is some workloads, and this is geometric mean across 55 applications. This is the performance improvement that you get in a single ranked DRAM system. And the performance improvement is 17% for these workloads. And you see that streaming, the workloads that benefit most are actually those workloads that do a lot of streaming, have a lot of row buffer locality, and have many streams at the same time. These are the workloads that get a lot of bank conflicts if you have few number of banks. And by decoupling a bank into subarrays, we're reducing the bank conflicts. So that's why, if you look at this, these are actually workloads from the stream benchmark. Stream benchmark is a common benchmark that's used to measure memory bandwidth. And those are the ones that fare really well. And streaming-like applications actually fare well. Random access applications get less benefit out of this. They get the benefit of parallelism, but they do not get the benefit of keeping the row buffers open. So looking at other policies, row buffer policies for those applications would be interesting. So how close does this come to the ideal? Ideal meaning making all of these subarrays independent. Basically, they're all you're increasing the number of banks. That buys you about 20%. So we're actually this mechanism gets most of the benefit of having more banks without the high cost of having more banks. So what is the cost of having more banks? So if you actually increase the number of banks by 8 times, you get 36.3% area overhead, according to our calculations. And this comes because you need to replicate the peripheral circuitry for each bank, which is the address decoders, as well as the other circuitry that you need to drive data out of each bank. Whereas with subarrays, you don't need to replicate that circuitry. We're just reducing the sharing of the global structures, and that adds some overhead, of course. Okay, a little bit more. This also actually reduces dynamic energy, as I discussed. Because you have multiple row buffers open, you can reduce dynamic energy in DRAM by about 19%. And this happens because your row buffer hit rate improves. Right? Your row buffer hit rate increases by 13%. And you can see more detailed results in the paper. Because you can take advantage of these multiple row buffers. Instead of trashing the row buffer, closing it and opening it because you get a bank conflict, you can serve from multiple different row buffers. Not at the same time, you have to switch using the designated bit latch, but you can serve from them, you can keep them open. Okay. Any questions on this? Yes? What about? So you get even better results with multi-core. You can take a look at the paper. But I think looking at multi-core, so this is an initial proposal. You can actually optimize how you map the data in multi-core such that they go to different subarrays. And you can design new scheduling policies that can take advantage of the subarrays. That's something we have not looked at yet, but that's an open area that can improve the benefits even more with multi-core. So it works for multi-core too, but you can do even better if you do nice data mapping and better scheduling in the memory controller. Yes?
You get these energy benefits if you build your DRAM that looks exactly the same as conventional DRAM and does it internally, and then just open and close subarrays internally.
Oh, internally. So that's very tough. That requires a lot of logic to be added into DRAM. And that's DRAM area is at a premium. You would like to manage this off at the controller. So basically, I think what you're saying is, why don't you implement all of this internally within the DRAM, the same ideas in the DRAM? You could do that. I think the downside would be the additional cost that you would get. The area cost would be much higher. But the same ideas are applicable within that domain too. If someone actually is willing to bear that cost, I think they can take these ideas and apply it within DRAM also. But I probably wouldn't recommend it given the history of what happened to DRAM. Because just to give you an example of a similar approach, not a similar approach, but yesterday we discussed the idea of tiered latency DRAM, right? We created a portion that's fast within DRAM. And that was actually made out of DRAM chips. We actually added an isolation transistor that has 3% area overhead. Previously, a long time ago actually, starting in the 1989, Hitachi was the first one, if I'm correct, developed a DRAM design that is actually cached DRAM. They called it the cached DRAM. And the idea was not only have a single row buffer that's required, but actually have SRAM within DRAM that caches many rows. And I believe they had a small structure that could cache 16 or 8 rows additionally. And this was a good idea because you could do caching. But the problem was adding this SRAM structure added a lot of overhead into DRAM. And the area overhead of that cached DRAM chip was very high. So it was very costly. And even though many different companies, I believe Hitachi, Mitsubishi, and one more, Toshiba, actually built these cached DRAM chips, and there are actually some others from Micron too, they're not used anymore because the cost is so high that people are not willing to pay that extra money for that cost. So there are ideas that can increase, that can be applied within DRAM or the controller or at different cost levels. You would like to minimize the cost ideally. And I think going forward, those ideas that minimize the cost in DRAM would be the most interesting thing. And if you have actually stacked DRAM stacked with a controller, you have even more opportunity to co-optimize the DRAM with the controller. But again, the DRAM process, the process with which you build DRAM chips is fundamentally different from the process with which you build logic. And if you add any logic into DRAM, it'll be inefficient. That, I think, fundamentally will not change unless we find a new way of manufacturing DRAM. Yes? So actually, I'll refer you to the paper. We can discuss in more detail. But we basically introduce a designated bit latch. That switch already exists today, except it's not controlled from outside. So there's a transistor that enables connection of the local row buffer to the global row buffers, except it's not controlled today. We're basically introducing that control. So we're not adding extra transistors. The problem, yes, you can say that now you're adding extra control, and that's the overhead that comes over here. Okay? So the paper has a detailed structure of how the DRAM operates. Actually, if you're interested in internals of the DRAM, I would recommend that paper, subarray level parallelism paper, that describes how those local row buffers get connected to the global row buffers in existing DRAM systems. It's very hard to find this information otherwise. I looked at many DRAM data sheets over the years, and none of them provide any of this internals, and many papers as well.